Testing, testing, testing. Testing, testing.
There it is. Hi guys, I'm Adam. I'm head of education. Sorry I was not here for the first 2 weeks, but I'm here now, and I should be here almost every Friday coming up. So yeah, I'm only gonna be able to be here till a little bit before 1 because I am on co-op, and this is my lunch break. So yeah, we're starting in 1 second once when the slides are ready. How long was the internet out, or was it internet, or was it just Wi-Fi, or what was that? Just the power? So everything's gone. Damn, that's wild. All right, you got it. You want to put it on this side when you're ready? All right, cool. Thank you. That's perfect. I can just press the button. Oh, Let's try changing slides. How are classes going? Classes going well? Yeah. All right. Good to hear. Good to hear. Hi, Lucas. Guys, is quarter zip season still here, or is it long coat season? Does anyone know? Quarter zip. There you go. I see this guy's a quarter zip. If not, yeah, we can. Is it working or no? It's not. I could share that. Or actually, it should be there.
Oh, your personal? Oh, sorry.
I also sent it in the e-board important.
Yeah. There's definitely a better way to do this.
Perfect.
Okay.
Are you able to read that?
No, obviously not.
You can always move that one to the other side if you need. All right. Did someone drop the sign in? Lead drop the sign in. Sign in is dropped. All right. You ready? Welcome to RITSEC, guys. All right. Make sure you join the Discord if you have not. Are you okay? All right. All right. Please sign in, guys. Sign in is dropped. We will be checking sign ins for when you want to get pizza later today at 2. All right. Check the calendar as well. Join the RITSEC mailing list. And now, guys, clap it up for the sponsors. There it is. All right. Keep it going. Keep it going. All right. Thank you, guys. Make sure you follow our social media. You guys can watch the stream on YouTube. Check out our LinkedIn and check out the Instagram. All right. And now for announcements. We have the last day of the mentorship signups. If you guys have any questions, I'm here. We have a few groups. We're kind of stacked now for one-on-ones, so I would definitely look into signing in for groups if you have not. We have some pretty cool advanced topics here, so if you guys are interested in like freelancing or maybe even like phone hacking, we'll see what you guys check that out. All right. If you guys, everyone is all good with the slide? Philip, you still scanning? No? All right. Philip could be your mentor, guys. All right. So we have applications for the CTF Black team as well. If you want to be a challenge author, sign up here. Also, this is the last day to sign up as well. See more at that website. DM OXM Malik on Discord. And also, if you want to be more on the dev side, check out the other QR code to sign up for be a part of challenges and setting up infrastructure. All right. We also have ISTS white team signups. Sign up here, guys. If you want to help out, if you maybe not a part of black team or purple team this year, check out, or blue or red, check out this. Be a white teamer, guys. If you don't know what white team is, you will be walking around during the competition, helping out blue teamers, and also setting up and tearing down the competition. You might also be able to help out black team with creating some injects. DM Leah right here. if you have any questions. And the competition date is February 27th to March 1st. All right, cool. And now, all new presentation, first time ever. Check out Web3 Security by Ariana Schwartz. Clap it up, guys. All right, we're going to fix one thing. So technical difficulties, guys. All right, favorite class this semester. What do we got, guys? Who's taking 201? Yeah, we have 201. Did they make it more difficult this year, or is it the same? Do you guys know? No? 'Cause I heard it was, I heard they changed the curriculum. So, like, I had, like, 4 tests, if I recall correctly, and now they made it where, like, in-person, like, handwritten tests. Am I right about that, or is that 202? If no one knows what I'm talking about, it's fine. But I'm not sure if the professor changed it. That's all I heard, guys. That's the RIT news from me. 5 more seconds, guys. All right, that's all I had. All right.
But now my thing went away. Where'd it go? We gotta come back.
All right. Another 5 more seconds. Does anyone know what Web3 security is? No? This is all new topic for people? All right. Well, neither do I. So that's why we're here, guys. We're going to learn what Web3 security is. All right. Who knows about crypto? Who knows about NFTs? Crypto NFTs, guys, right? We're looking at the what is that NFT called with the chimp? What is that called? Dumb chimp, or what is it called? No. No one who has an NFT here. Who has Bitcoin? Who has any cryptocurrency? There you go. All right. So we're going to look into that a little bit. All right, guys, you don't gotta listen to me anymore. There you go.
Thank you, Adam. Hi guys, I'm Ariana. Sorry for the wait here, but we're gonna get started with Web3 security. So, a little bit about me is I am a master's cybersecurity major. I'm on my last semester of BSMS. I'm the former RITSEC CA, so hopefully you kind of know who I am already, at least a little bit. And then I'm also a member of WIC and Gymnastics Club. So what we're going to talk about Okay, there we go. Okay, so what we're going to talk about today, we're going to talk a little bit about an intro to Web3. So what is it? What does it do? And then some, like, very high level, low level blockchain, if you will. And then we're also going to talk about securing Web3, so new risks, familiar vulnerabilities, and then how to secure Web3 products. By the way, we're going to move through like a lot of stuff really fast. So if you have a question, just ask it when you have it. Don't wait till the end. We're going to be so far past whatever your question was by the end, so don't wait. Okay, just like a heads up, I realize there's a lot of ways you can lose a lot of money in these presentations. So like, I don't recommend you do anything I say necessarily. And if you want to go trade crypto on your own time, that's fine, but it's not my fault if you lose money. So yeah. Okay, so who knows what Web3 is? Even though Adam just like asked that, but I was busy, so I don't know what he asked. Okay. So Web3 is this new evolution of the internet, according to Chainlink, where it's centered around decentralization. The idea is that you have a similar to our current web experience, but it's centered around ownership and cryptographic guarantees. So basically, we want similar internet experience, but on the blockchain is like the idea. And Web3 is kind of becoming more mainstream now, so I really recommend getting into this area right now. Okay, so some pros of Web3. We're going to go over pros and cons. First pro is resilience. So Web3 is decentralized. So over here we have, this is a centralized network. Obviously, this would be like your regular internet, and then this is a decentralized network. So this would be like your blockchain, right? So on our centralized network, if we were to, let's say the white dot is like Google. If Google were to like completely crash, it's down, it's gone. This is like the end of days, right? Like we're done. It's over. Okay, it's going to be tragic. Now, with our decentralized network, these nodes could be anyone. So, like, maybe one is like a company, maybe one is like, I don't know, your friend or something, okay? Maybe someone here decides to host a node or something. You can. It's just like you make a little cache. It's kind of cool. Maybe someone here decides to host a node, but they do it on the stack, so it like crashes, right? Because, you know, if your node crashes, that's bad for you, but like the rest of us, we're going to be okay. It's going to be fine. It doesn't really affect the entire network just because one person's node goes down. Transparency is another big one. So if it's a public blockchain, anyone can see the code for smart contracts and also the blockchain itself. We're going to talk about this more, but basically if you think there's something sketchy about a contract you're thinking of interacting with, you can just go read the code and see for yourself if it's a problem or not. Sorry. Okay. Next thing. Yes, there we go. Next pro is that you have control on the blockchain that you don't have on the regular internet. So you have control over your data, your digital assets, and your identity more so. So with your data, decentralization prevents one centralized entity from holding all of your information because there is no like overarching authority that could be collecting your data. There's also peer-to-peer interactions on the blockchain. So when it comes to like paying people or something like that with your digital assets, there is no middleman. There is no like you're sending your money through a bank or something. It's I'm sending money from my wallet to your wallet, no in between. And lastly, you have more control over your identity. So there's a thing on the blockchain called self-sovereign identity, SSI. This gives the user more control over their information because of you keep your information in your wallet. And if someone needs to know your age or something, you can choose just to send over that piece of information to whoever it is. And again, there's no middleman, there's no overarching authority, so no one's going to be collecting your information. Okay, there are also some cons. A big one is complexity. They're trying to make it more user-friendly. They're trying to make it more mainstream, but your grandma is not using this anytime soon, or at least mine isn't. I don't know about yours. Also, security is a concern, and I know what you're thinking. Then why are we talking about it, right? We should probably just not do this at all. But anytime there's a new thing, there's going to be new problems, right? And I want to ask you guys right now, what is the biggest vulnerability for any system? Humans? Right. So the biggest concern for Web3 is actually that people are going to do stupid things. You have, with your crypto wallet, you have a public key that's public, right? Anyone can see it. Anyone can like send you things with your public key, okay? Then you have your private key. Your private key proves your ownership of the wallet. If you lose your private key, you have lost all your money because you cannot access your wallet anymore. Okay, so think of like, it's still there, you just can't touch it. It's like if all your money was in a bank vault and the bank vault was sealed and I threw away the key, you know exactly where it is, but you're never gonna get to it. It's kind of like that. There's also a concern with phishing, like there always is. If you give someone your private key, you gave them all your money. It's okay, we all make mistakes, but that's a pretty big mistake to make, and it is a very big concern, especially if you're trying to make this mainstream, you're trying to get less technical people into it, and when you get less technical people into these things, you run into these problems a lot more. I would also like to say with the phishing, did anyone hear about the Bybit hack last year? They lost like billions of dollars, a little bit. Yeah. So billions of dollars, that all started with a phishing call to, now that was an organization, so it's a little different than like you as a person, but it all started with a phishing call. Places don't hack the wallets themselves, they hack the people. Also, if you have your self-sovereign identity information in your wallet and you give someone your private key, congratulations, you just gave them your whole identity. So you really got to be careful with that. There's also a couple other things you have to watch out for, like rug pulls. These are pretty much just like on-chain scams. One example is like with these meme coins. A lot of time people buy these like influencer meme coins or whatever, and then whoever posted the coin can just kind of drain all the liquidity, and you're left with this useless thing and no money, and you paid whoever whoever made it up, and they're rich now. So last is regulation. So public blockchains are open source. There is no governing authority over it. And also, as far as like regulation in the government, the policies we have for the current internet really do not apply very well to Web3, and we're starting to see more regulations already, but we're probably going to start seeing more, I would assume. Okay, now what does Web3 actually do? So, like, now we know what it is, but what can we do with it? So the first thing is cryptocurrency. We can have money online. It's cool. I'm going to say this now, like, Bitcoin is not technically Web3. We'll get into why later, but it is cryptocurrency. So in case you were wondering, these currencies are Bitcoin, Ethereum, Solana, USDC, and Tether. USDC and Tether are both stable coins, which means they are one-to-one with the US dollar. So this is like literally just online money. Okay, it's just digital money. If you were to like pay a business with USDC, that would be more ideal for the business probably than paying them in like Bitcoin, because the thing with Bitcoin, Ethereum, and Solana is that their prices depend on demand. So the stable coins, like it says, they're stable. They're going to be whatever US money is. These other coins are kind of similar to stocks, where like the more people who buy them, the more expensive they get, and the more it's selling, not the more it's selling, but the more people are getting rid of it, the less it's going to be value-wise. And this is like where I think a lot of the ideas of like trading crypto comes from, is the volatility of the money. Does anyone own crypto? I think Adam asked that too, but I wasn't looking. Yeah? Yeah. I'm just curious, and I didn't see who was answering. Okay, so another thing you can do with Web3 is decentralized finance, and we're going to talk about really quick just like what some attributes are, and then we're going to talk about what you can actually do with it. So first thing with decentralized finance is self-custody. With normal money, a bank holds your money for you. With crypto, you have the option to hold your assets yourself in your wallet. We already talked about why you may or may not want to be careful with that. Or you could choose to entrust your assets to an exchange, and they kind of hold it for you. But that comes with its own risks because, like I said, there are attacks, like an exchange could get hacked and their money could get taken too. Next thing with DeFi is that transactions are immutable. So once an action is on the blockchain, which means they're either mined or validated. We'll get into what that means in a minute. But once it's on the blockchain, it's always there and it's always visible. So if I said I paid Leah for dinner and she says I didn't, we can just pull it up right now. Like, it's like Venmo, but there's no like cute little message, you know? Okay, next is it's peer-to-peer. So we already talked about this, but there is no one in the middle. There's no bank it has to go through, nothing like that. It's just my wallet to your wallet, and that's it. Open source, we also talked about this, but code for contracts are always visible. You can always check them. And then code for the blockchain is visible, and technically it's open source. So if you had a really good code idea for the blockchain, you could try to get it accepted and submitted like OpenSSL or something else that's open source. And then it's also digitally native. This is not the same thing as like, oh, I have my banking app on my phone and I click buttons on my phone and it like transfers money to my accounts or whatever. No, there's like a physical back end to your banking app on your phone. With decentralized finance, it's digitally native. It's all online. There's no like physical process on the back end. So what can you actually do with decentralized finance? This is where we get into things that you can lose a lot of money doing, so I would be careful with these things, but you do you. First thing is trading. There's a couple of different ways you can do trading with crypto. You can do spot trading. That's where you buy and sell crypto depending on the current price, and this is very similar to like stock trading in concept, not necessarily in execution. And then other things you can do with trading is there's derivatives. So derivatives are contracts that are dependent on the value of the cryptocurrency. There's two types I'm going to talk about, but I think there's like more in general. One is futures. This is when you bet on if the price of an asset is going to increase or decrease. So if you bet that it's going to increase, that's called going long. If you bet it's going to decrease, that's called shorting. These have an expiration date, and when you hit that expiration date, if your guess was right, then you get paid. If your guess was wrong, you have to pay, basically. So you're just betting on the price of the asset. Then there's something else called options. This is similar to futures, but the trader has the right but not the obligation to sell. So you don't have to pay right away, like if you're wrong or whatever, but this contract does still have an expiration date down the line. Like you can sit on it for a while, but eventually it's going to expire. They are time bound. So eventually, if you're wrong, like if you're that wrong, you're going to lose money anyway. Next is yield farming. This is when you lock up coins for some reason, and then it gives you profit for that. So an example of this is a lot of DeFi platforms like to increase market value by incentivizing that users lock up their coins. They do this because of, like I said, the more people who are getting rid of the coin, the less value the coin has, right? So by locking them up, you're not selling them. And in return for locking up your coins, you would get some reward for it. And I think there's other reasons to yield farm other than that. There's just an example. Okay, next is liquidity contribution. So decentralized exchanges need liquidity pools. This is just like they're holding coins for things like token swaps or lending, which we'll talk about lending in a minute. And this is how they guarantee that they have these coins on hand for these actions. If you allow your coins to be used in the liquidity pool, then you'll get some sort of reward in return. You'll probably receive payment in the form of like a portion of the trading fees. And then you can also get some other rewards. One is you can get a liquidity provider coin. This has like your share of the pool on it, and sometimes you get paid dependent on your share. So like someone who has 50% of the pool is going to make more off of the same whatever than someone who only has like 25, if that makes sense. Also, liquidity provider coins can be used for yield farming, which we just talked about. If you lock up your LP coin, then you would make more money off of the same thing other people are doing just because it's like a special coin, if that makes sense. And then also you could get a governance coin. So people who contribute more to these platforms could end up getting voting power because of it's decentralized. Like no one's making the decision for you, so they let the users get voting power. But you have to contribute more than just being like a regular user. That's why you have to like earn a governance coin, you earn your vote. Next is lending and borrowing. So if you're looking for student loans, this is definitely not the way to go. But a simple example of this is you literally just put your crypto that you already own up for collateral, you take out that money, and then you would gradually pay back your loan. And as you pay back your loan, you would get your crypto back. If you don't pay back your money, then you don't get your crypto back because that was your collateral. And there are a lot of other ways you could do this. This is just like, again, just an example. Okay, tokenization. I really like tokenization. I think it's really cool. I think if there's one thing you take away from this, it's that like I feel like this is I think this is like the future, honestly. Like it's really okay. These are baseless statements, but I think it's cool. So basically tokenization, it shows ownership of a physical asset on the blockchain. You can make transactions involving assets way simpler and faster than you could in the real world. And this also lowers transaction costs. All of these things actually increase the value of the assets. So what are some things that you can tokenize? Like really cool stuff. First of all, commodities, which is like precious metals, oil, agricultural products. You can tokenize that. You can tokenize real estate. You can tokenize stocks, which I think is really cool. Luxury goods like art and collectibles. There's talk about like intellectual property tokenization. Like these are all really cool stuff. Again, this is not super mainstream right now, but it is like really cool, and I think it's somewhere that we could go with it. I don't know. Then there's flash loans. I hate these things. They're kind of confusing. Basically, how flash loans work is it's an uncollateralized loan where you borrow and pay back funds in the same transaction. So just to kind of define that a little bit, by uncollateralized, I mean you don't have to put up money for this loan. You don't have to put up money because of you're taking out and putting back the money in the exact same transaction. So if anything goes wrong in there, if you don't pay it back, whatever, the whole thing gets reverted. Okay? People use this to take out a lot of money at once because you don't have to put up collateral for it. I don't need $10,000 to take out this $10,000 loan, is the concept. People use this for a lot of things. We're going to talk about how it can be used for an attack later. But for now, an example of this that we can talk about is arbitrage. So basically, you take out a flash loan, right? You buy crypto on an exchange where it's cheaper, and then you sell on an exchange where it is more expensive. Then, in the same transaction, you're going to pay back that loan, and what you're left with is the difference between the crypto on the different exchanges, if that makes sense. Does that make sense? Yes. Okay, cool. Making sure. There are also, like I said, there are also other ways you can use flash loans, and we'll talk about like one of them later. You can use it maliciously, but okay. So, NFTs. NFTs are certificates on the blockchain that prove ownership of an item. This is like the art version of NFTs, but they're actually used like on a technical level. They're used for a lot of other things. They can be used for like your tokenization stuff. It's just used to prove your ownership of something unique. Okay? They have to be distinct, that's the whole point, and they are stored using a unique identifier, which is what makes them unique. And this is I think the art version of NFTs is cool though, so I am going to talk about it for a minute. Does anyone want to guess how much any of these cost? These are all NFTs on the blockchain. Lucas said $1 million. 1,035. You would think, right? Okay, these are extremely expensive. Someone made $52.7 million for putting words on a black background. I have so many words on a black background on this screen right now. Like, this is crazy. These things are actually expensive. They do actually have value somehow. I don't know. But just like, I just want to explain why it's not completely useless, because they do actually do something. So, does anyone think they're useless? I know I just said that was a lot of money, but does anyone still think they're like stupid and useless? Yes. Okay. Yes. No, this is my Discord profile picture, but I needed like an example. Okay, so basically that's me. That's my NFT I made, and then this guy wants to buy my NFT, right? So it's like simple, just pays me. I'm surprised this transition worked that well, honestly. Okay, so now I have coins. He has the NFT, right? And I understand everyone thinks that's stupid, because why does he want it? But I think what we're missing is that, like, we already do this. Because, like, what if I was, like, a better artist, right? And then he bought, like, a better picture, and then it was for, like, cash. So we already do this. It's just buying. It's buying art. That's what it is. That's all it is. So just to be clear, a couple, like, ground rules, I guess, to make sense for NFTs. Person who bought the painting owns the painting, right? Same thing. Person who bought the NFT owns the NFT. Just because, like, I can buy a print of Starry Night, that doesn't mean I own Starry Night, right? It's the same thing. Just because you can screenshot an NFT doesn't mean you own it. That's the value in having it, okay? And then also, just to clear this up, because I think this comes up a lot, Starry Night is not technically copyrighted, but even if it was, this guy would not own the copyright to Starry Night just because he bought it. It's the same with NFTs. Just because you buy an NFT does not mean you own, like, the copyright ownership over it. You just own, like, the art itself. So, yeah, I don't know. Does everyone still think it's dumb? Or, like, does it make slightly more sense, at least? Okay. Okay, thank you for your opinion. I don't think it's dumb. If you still think it's dumb, what if I told you that NFTs have real-world perks? Not all of them. Some of them. Good amount of them at this point, I would say. So, sometimes proving your ownership of an NFT can get you something else. Like, maybe it gets you perks in some sort of game. I don't know, maybe like a new skin or some sort of like power up, whatever the game is, I don't know. And then it can also get you access to exclusive events. So this is a real NFT. Yeah, see, he knows. It's a real NFT, and it gets you into real actual events in real life. So this is like a reason people will buy them, is because it's not just like the art thing, even though you would own like the art, but there's more to it. Moving on from my rant on NFTs, just because I feel strongly about it. But there are other things you can do on Web3. So DApps is a big one. These are decentralized applications. They're applications that are coded in smart contracts, and they are put on the blockchain. And they can do pretty much whatever you want. You're just coding on the blockchain. So some examples is Decentraland. That's a world-building game. We have Upland, which is a virtual real estate trading game. You buy, it's very weird. You buy real estate that is real in the real world, but you don't buy the actual real estate in the real world. It's just like a virtual world where you own buildings that are real, if that makes sense. I don't know, it's kind of fun. There's also music apps. So this one that I have on the screen is used for helping artists connect with people who actually listen to their music. And then you can also do gambling on, everyone just looked up right now. I don't recommend this again. I don't recommend you do this, but you could do gambling with crypto. This is Polymarket. It's very funny. You can do everything from sports betting to betting how many times Elon Musk will tweet each week. Everything's on there. Yeah, it's funny, I think. Okay, there's a lot of other things you can do as well. One is there are decentralized autonomous organizations. So I talked about this with the governance coin, but a lot of times decentralized exchanges will let members make decisions for the platform. There's also soul-bound tokens. So these are non-transferable. They can represent achievements, your identity, your credentials. And this is where self-sovereign identity comes into play. And again, it's not super mainstream, but it's kind of up and coming. There's also cloud storage, which I thought was really cool. So Filecoin is a decentralized storage network that's used for your cloud storage, which is just so convenient and cool. The Brave browser actually uses, I didn't realize this either. Brave browser actually uses Web3 a lot. First of all, they pay their users in crypto for watching ads. They reward publishers with crypto. They protect your identity using a decentralized identity model, which is how they do that. They have an on-chain naming service. I don't know this much about it. I try to do research, but it was a lot. They just do a lot. They also have their own Brave crypto wallets. So yeah, if you want to look more into that, it's actually very interesting. I didn't realize they implemented that much, but they do. And then also there's oracles. So these allow you to use real world data on chain. So for example, we just talked about Polymarket. They get information on the outcome of a sports game or something from an oracle. That's how they determine what actually happened in the real world. And we're going to talk more about those later, so try to remember that. Okay, so really quick, we're just going to learn a little bit about blockchain technology. I'll keep it really high level because, So there's two different ways you can mine or validate coins or transactions on the blockchain. One is proof of work and the other is proof of stake. So first, we're going to talk about proof of work. This is used by chains like Bitcoin, Dogecoin, and Zcash. So pretty much your sender is going to send their coin to a receiver. And this gets you, first of all, there is a transaction fee with that. So you need to keep that in mind. And then also this gets you transaction information. That transaction information gets sent to the mempool. Okay. Next, what's going to happen is your miners are going to select transactions that have the higher transaction fees associated with them. And what they're going to do is they're going to take their selected transactions as well as the hash from the previous block, because this is where we get the chain aspect of the blockchain. So you use the hash from the previous block in your new block to connect them. Each block has a secret nonce, which is hashed with the block header. So what the miner does is they are just over and over and over again, they are hashing the header with this nonce, and they're just trying to guess the nonce. It's just brute forcing, pretty much. Now, what you have to keep in mind is that you're competing with other people who are also doing the same thing. They might have a more powerful system. They might pick a different starting number that's just closer to the nonce. It really is very arbitrary at a certain point. And they're just going to repeatedly hash the the block header and the nonce, and Bitcoin uses SHA-256. In the end, one miner will be able to add their block to the blockchain when they guess the correct nonce, and this will in turn earn them the transaction fees from the block along with some extra Bitcoin. And this is not energy efficient at all. People have like huge data centers where this is all they do. It's such a waste. Yeah, I don't know why Bitcoin still does it, but then other platforms such as like Ethereum used to do it, and then they switched over to proof of stake, which is what we're going to talk about now. So proof of stake starts out the same, right? You have a sender wallet, you have a receiver wallet. You're going to send your Ethereum, right? And, this also use, like, examples, Ethereum or Solana, both use it, also a bunch of other platforms. Again, transaction has a transaction fee attached to it. Transaction fee is chosen by the sender and is also paid by the sender. And in Ethereum, this is referred to as gas. So if I say gas, is what I'm talking about. It's the transaction fee. So this, again, you have your transaction information, gets sent to the mempool, right? We already talked about this. We're experts on that part. This is where it gets different, okay? So what we have on Ethereum is we have multiple validator nodes that have staked their Ethereum. So pretty much they put up, it's a minimum of 32 ETH. They put up their minimum amount, and they say, I want to be part of the validator thing, okay? They want to do it. They want to participate. What happens is that now you can actually stake more than just 32 ETH. Before, it was just like minimum and maximum was 32. Now you can stake more. I don't know what the maximum is off the top of my head. If you stake more, you're going to be more likely to be selected to actually validate a block. It's not because of there's a bias towards people with more money. It's because of kind of like a raffle. If you have more tickets in a raffle, you're more likely to get picked. It's like the same concept. So basically what happens is you're going to select one node who is going to get to propose a block. So we're not racing. Not everyone's trying to do this at once. We're not wasting energy. One person is going to propose one block. That's it. Okay? So this selected node is going to choose transactions from the mempool, which have the highest transaction fee, because that's how they get paid the most money for proposing the block. Okay, so now they're proposing their block, and what happens next? Well, we want to make sure it's right? So now all the other validator nodes get to vote on if we actually like the block or not. If you're trying to do something malicious, then they'll catch you on that. That's the point. There's like checks and balances here. So if everyone likes your block and they vote that it's okay, it's valid, then you have a valid block. Congratulations. You get your Ethereum. Again, it's your transaction fee reward, and all is good and fine and dandy. We'll go back for the next block and someone else will get picked, and it's fine. If you try, maybe, I don't know, maybe you suck at setting up your node, maybe you tried to lie or something, whatever. If it's voted that your block is not valid, then the ETH that you have saved up in your stake will get slashed. So they will take, it's usually about like a little bit over 1 ETH they'll take out of your stake because of you did something wrong and you're being like punished. That's your consequence for not doing it correctly. And that's why you have to have that money locked up like that. Yeah, and that's how, I don't know, that's it. That's how the blocks are made. Does anyone, before we move on, does anyone have any questions about proof of work or proof of stake? Okay, cool. All right, so what are smart contracts? Like total 180 right now. What are smart contracts? It's literally just code on the blockchain. Like that's it. You code things, they go on the blockchain. Yeah, I don't know. It's not that complicated. It is that complicated, but like not anything we're gonna get into today. Smart contracts, by the way, on Web3, just like a transaction, it gets like it's part of a transaction. Once it's validated, it would be validated. Then it's on the blockchain forever. It can't be taken off. So some smart contract coding languages, we have Solidity and Viper are very popular. Solidity is very similar to Java. I'm not saying it is Java, it's just like similar. And then Viper is more similar to Python. Some blockchains also use Rust. So if Rust is your thing, you could Yeah, like people here use Rust. So if you like that, I think like Solana, you can code smart contracts in Rust. Yeah, those are just some things you can get into. Web3 platforms. I talked about this earlier, but Bitcoin is not a Web3 platform actually because the the Bitcoin blockchain does not support smart contracts. So all you can really do on there is your like transaction stuff. And since there's no smart contracts, there's no dApps or anything like that, and therefore it's not really like this whole like Web3 environment thing. It's just like money transactions. Okay. Any questions about anything about Web3? Because I'm going to stop explaining Web3 and only talk about like security the rest of the time. Also, I hope you enjoyed the pictures because there's like no more. Okay, so really quick, I've said this like 3 times, but big new risk, their smart contracts are publicly visible on public blockchains. So anyone can look directly at the code for your dApps. If you write bad code, everyone will know, and they will know exactly what to do to mess with your stuff, okay? So this is positive. It creates a lot of trust. If anyone can see your code, like I said, anyone can determine if it's safe or malicious. It also is good for decreased fraud because if you post a malicious smart contract, other people are going to be able to see it. They're going to catch that. It's going to be obvious. Hopefully it's obvious. Maybe it's not, and they're really good. I don't know. Also, a little negative. It's not great for privacy sometimes because of all of your transactions are super public. So if you were like a business trying to make some transactions that you don't want everyone to know about, that's unfortunate for you. Everyone can see it. Also, code visibility is just kind of a vulnerability for code because if you've turned like a black box type of thing into they can fully review your code. If there's a problem with it, they're going to find it way easier now. But let's get into these are all like smart contract vulnerabilities. So if you were like coding a smart contract or like reading a smart contract for someone else or whatever, these are things that you want to make sure you avoid. And there's a lot that actually overlaps with like concepts we already deal with all the time. So first is logic errors. This is like obvious, okay? Smart contracts, they have a lot of math going on. You want to make sure your logic's correct. This could end up leading to like incorrect rewards. Maybe you're like paying people too much or too little, or maybe your lending pool doesn't have the correct amount in it or something like that. Impact of this, you can lose money, or maybe your contract doesn't do what it's supposed to do. And this is really easy to fix. Just check your code, like make sure it's correct. And then also, you can use pre-created libraries and code snippets. So like there's no need to reinvent the wheel here. Like if it's a mathematical operation, just use a math library. Next is insecure randomness. So on Solidity, with Solidity, you cannot generate true random numbers, unfortunately. And this leads to a lot of people using pseudo-random numbers that are generated using some sort of information on-chain. We're going to kind of like touch on this with like very specific examples later, but just for right now, using things like block timestamps, block hashes, or the block miner address are bad ideas because they're things that could be manipulated or they're things that could be predicted. So the impact of this is, yes, they could be predicted. Remediation, use off-chain factors. So we talked about oracles earlier. If you wanted something very random, you could definitely use some factor outside of the blockchain that someone couldn't control or that someone couldn't easily predict. Or you can actually use, there's a random number generator for smart contracts that's called Chainlink VRF. That's also another option if you want random numbers. Like there's just really bad idea to use on-chain controllable or predictable things for random numbers. So next is lack of input validation. This is when a user inputs like a not checked value, and then obviously it leads to some sort of unexpected outcome. Some examples of this is there might be like a missing range check. So if there's like an unreasonably high or low value, that could break the contract. Also with balance validation, you don't want someone to transfer more money out of their account than they have, right? Unchecked zero address is an interesting one. So the zero address is like a wallet that no one has the private key for. As we talked about earlier, if no one has the private key, no one's touching anything in there. So someone could like send money to this 0 address, and then it would just sit there and no one can touch it. I don't know, like, just to be mean, pretty much. I don't really understand why, but once it's sent there, it can't be recovered, and it's, like, kind of annoying because then nobody's touching it anyway. Then also missing authentication, so this could, like, let non-authorized users execute some sort of, like, privileged command or something. And for remediations, you should really only allow expected inputs within an expected range and format. This is very similar to, like, regular web concepts we talk about a lot. And then you should require user authentication for certain actions so that people aren't accessing functions they shouldn't really be touching. Another one is denial of service. Like, we all know these. Like, it's so transferable, right? So you're just exhausting contract resources. This could be, maybe it's contract, it could be gas, it could be the storage, or it could be the contract logic. And you're just going to render the contract unusable and maybe lose some funds in the process. And then remediation for this, like, you want to limit gas usage and you want to avoid unbounded loops. So with the unbounded loops, the idea is, like, someone could just run your contract so nobody else can use it, obviously. Okay, next we have integer overflow and underflow. This one gets a little funky because there is, like, in the newer versions of Solidity, they have, like, a solution for it. In older versions, they don't. So keep that in mind. But basically, overflow or underflow, you're either adding to the maximum amount of an integer or you're subtracting from the minimum amount of an integer. So if you have an unsigned integer that the max is 255 and you add 1, if you're using a version of Solana before 0.8.0, then it's going to wrap around to 0 as the value. 255 plus 1 would equal 0. And then same thing if you're using an older version of Solidity, then for an unsigned integer, if you subtract 1 from 0, it's going to wrap around to 255. If you have a newer version of Solidity, both of those are going to revert the transaction. It's going to fail. It's okay. But it leads to a lot of, like, contract manipulation, especially when subtracting gets you, like, a higher number. And then you also have to consider that this goes back to the input validation thing. You really should be making sure the input is valid before it gets this far that it allows, like, a wraparound type thing. But yeah, anyway, remediation. Using the newer version of Solidity, definitely better. The newest version, we're at 0.8.33, so there's, like, a lot of options in between 0 and 33 you could choose. And then you should use math libraries also. Talked about that before. And yeah, input validation too. Okay, access control. Basically, this is when your user's identity is not checked correctly or restricted, and you allow some sort of unauthorized action on your smart contract. So an example of this is there's, like, an owner-only function, but anyone can run it. Well, then it's not owner-only, everyone can run it, and this is going to cause a lot of problems. So impact of this, an unauthorized user could access some sort of restricted either data or a function. Probably you're going to lose money. Probably the contract's not going to do what it's supposed to do. And remediation, the first one on here is actually a little interesting. So you need to secure the initialization function of your contract so that it can only be called once. This is very interesting. There is an initialization function for the contract, and if you don't make it so that it's only run once, then an attacker can run that function again, and they will take ownership of your contract. So you want to make sure, like, when you initialize it, that's the only time that's ever run. Okay, and then this is just, like, if you have some sort of application that has a front end on the regular internet and then has some sort of, like, on the back end smart contract, whatever going on, you need to also make sure that your front end regular web application is also secure. If you don't, then it doesn't matter how secure your smart contract is. They're going to manipulate it on, like, the front end, the regular web end, and do whatever they want anyway. So, like, some examples, people have used, like, cross-site scripting, cross-site request forgery, or SQL injection to kind of circumvent whatever securities you have going on your smart contract. Yeah, it's just, like, I mean, it's obvious, but it just needs to be said. So your front end needs to be secure as well. Okay, now new vulnerabilities, getting interesting. These ones are not something you would have, like, seen before so much. So first one is reentrancy attacks. This is when you have a function that makes a call to some sort of external contract, and before it updates its own state within the contract, it makes that external call. What that does is it allows the person to keep calling over and over and over again that external contract. So an example of this is you have this external contract that is just repeatedly making withdrawals until the smart contract is drained of all its funds. And you're able to do this because of your initial smart contract is never registering that it's actually like made that call and it's done. So I saw online, this is like a very cool idea, I guess, that all of your functions should follow the order of check, effect, and then interaction. So first, you want to check if there's any sort of conditions. They need to be validated first. Then you want to update your smart contract state. After you have updated the state of your smart contract, then is when you want to actually execute the external call. If you do it in the other order, that's what allows the reentrancy attack. And some remediations for this, you can update the contract state before making external calls, like we just said, and then you can also use reentrancy guards. So what these do is they lock the function during execution so that you can't make more calls on the function until it's completed running. Okay, next we have unchecked external calls. This is like very similar, but not exactly. So what this is a contract makes calls to an external contract, like we said, but it neglects to check that the return information is like valid before processing it. This goes to like input validation also. So basically you make this call to an external contract. If it results in an error and you're not checking that, then you're just proceeding with this invalid error through the rest of your contract. And it's not going to run properly. It's probably going to have some sort of inaccurate contract state. And also it just opens opportunities for other vulnerabilities to be exploited because of now like your contract's not running properly. So how to remediate this? You want to check the return value and implement error handling. And then also there's this really cool transfer function that actually like looks out for this. So the transfer function will revert external calls if they result in an error. If you use a function like send or call, it will not do that error handling for you. Okay, next is gas griefing. So if you remember, gas is like transaction fees, right? So what this does is an attacker provides enough gas to execute an initial, your initial, like if you have one smart contract, it has enough gas to execute that one, but any sort of subsequent external calls, there's not enough gas to execute those. So an example of this is like contract A is supposed to make calls to contract B, but I only give enough gas to execute contract A. Then the call to contract B is going to fail, and then you run into issues that we just talked about with like your unchecked errors and stuff like that. So remediations, a lot of remediations are like the unchecked external call kind of remediations, and then also you need to check the gas before making the call. It's hard to set like a minimum gas amount for a contract because the price of gas changes. Not the price of gas. The amount of, yes, the price of gas changes. So what happens is if the blockchain is more busy, like there's more going on, more people have their transactions in transaction pool, then you're going to need to provide more gas to do the same function if you want it to actually be executed in like a timely manner. Otherwise, if the blockchain's busy and you don't give enough gas for the like busy amount or whatever, then the transaction is just going to sit in the mempool until it's like the only one left, because if everyone's going to select the transactions that have more gas attached to them before yours. That was like very poorly explained, but I don't know if it made sense. Basically, like if the blockchain's more busy, then you need to give more gas for the same thing than if it was less busy. So that's why it's hard to set like this minimum amount. Okay, next is Oracle manipulation. We talked about oracles earlier, but as a reminder, oracles allow you to use real-world data on-chain, and smart contracts often use this information to trigger certain actions. So if an attacker manipulates the information coming from an oracle, then they could cause the contract to trigger some action when it shouldn't. An example of this, like a very highly conceptual example of this, is like, let's say there's a sports betting contract. You bet a certain team is going to win. Maybe you thought the Jacksonville Jaguars were going to beat the Bills, because I did. And when they lost, instead of losing your money, you just like sent fake data via the Oracle to the contract, so you got the payout as if the Jacksonville Jaguars won, even though they did not. Okay, that's very conceptual. How it's actually really used is with flash loans, which is what we're about to talk about. But the idea is there that basically you're trying to feed the contract this false information that didn't actually happen, so you'll like trigger whatever action it is that you're trying to trigger. So remediation for this is you want to get data from multiple reliable oracles. There are cases where some contract is using like a very unreliable oracle, and you can like really manipulate the information, but for the most part, like you're not hacking an oracle, right? This is how it's actually really usually used. So reminder really quick, flash loans are loans where you withdraw money and you pay it back within the same transaction. There is no collateral that you put up, so a lot of people use this to take out very, very expensive loans, very high value loans. And if you think back to the arbitrage example where we took out a loan, we bought crypto on exchange where it's cheaper, right? And then we sold it somewhere it was more expensive. And then we repaid the loan, we kept the difference, right? That's what flash loans are used for sometimes. However, they can also be used to help an attacker manipulate blockchain logic in their favor to make the contract do something. So basically, an example of this is, let's say you have a smart contract that pays out if a certain coin reaches this certain price, right? Well, an attacker can take out a very big loan. They can put all of their funds into that coin, and then they would take the payout from the contract, right? Because of however big your loan was, it made the coin reach whatever price was on the contract. Then you would return the loan, and the price of the coin would like automatically go back down to what it just was. So you got the payout from the contract because of the price of the coin reached the price of whatever the contract was waiting for to pay out, but it didn't really reach that price because then it immediately went back down to what it was before. This is not something that's like unintended use. Like, okay, the argument with the flash loans is that they suck because of your contract is going to lose funds when the thing didn't actually happen. Other people can also lose money, which sucks too. It's very mean. But the argument with the flash loans is that they don't technically do anything you're not allowed to do. However, you can still code to protect your smart contract from falling victim to this. You should use reliable oracles, so they should be either decentralized, which means that they take information from multiple sources instead of just one, and then they come to a consensus. So if you did that, then even if you were very temporarily manipulating the price of this coin, right? So if you use multiple oracles that are all taking this consensus, then it probably would not register, like they would not all agree that the price of this coin was actually that price. And then similarly, you can use an oracle that implements time-weighted average prices. So this means that the oracle takes the average price over multiple blocks or minutes. So just because you, like, for 1 second made the price of this coin, like, super high, it wouldn't stay that way long enough for, like, a couple minutes to go by with it being that price. So it wouldn't ever register that you actually did that, really. And yeah, so basically the idea with the remediation is you want to prevent a single temporary transaction from impacting the value that is like read by the oracle. Okay, next is force feeding attacks. So you're forcing currency into a contract which is not supposed to accept it. Maybe it's not supposed to accept currency at all, or maybe it's just not supposed to accept as much as you're feeding it. An example of this is maybe this contract has like a game where, you know, everyone can only submit 1 ETH at a time. Whoever submits like the 10th one gets a prize, whatever, right? And then it's at like 7 ETH and you force 3 in. And then you get the payout and you won even though you like broke the rules of the game, right? So the contract balance will check because technically the balance of the contract is correct for the payout, right? It's correct for the reward. But what you don't want to do, and this goes back to something we had talked about earlier, what you don't want to do is you don't want contracts to do things based on the price of the contract, because it's something on chain, it's something people can manipulate. The impact of this is that you're going to end up like paying people you don't want to pay, or maybe you could even like lose the functionality, the correct functionality of your contract. So what you don't want to do is you don't want to rely on the balance of the contract as a check. And it like kind of relates to the insecure randomness we talked about earlier, because of, again, it's like that it's on chain, people can do something with it. Next one, access control, but different access control than what we talked about before. So basically, on public blockchains, we said this, smart contracts publicly visible, okay? Hard coding any sensitive information or non-public information, doesn't even have to be that sensitive, would allow anyone to see it. So if you hard code your password, you hard code private API keys, you hard code some sort of admin address or whatever for your internal company, everyone can see it now. Those things are burned, they're gone, they're done, okay? You need to change them immediately. Everyone is going to attack your stuff. So this is really bad. Also, just anything sensitive you don't want to put on there, because that's information leakage. And it can lead to unauthorized access if you have like important passwords, or like I said with the APIs. Remediation, you never want to hard code sensitive info on your smart contracts, ever, ever, ever. What you want to do instead is you want to use some sort of off-chain storage that will fetch the information, that your contract will fetch the information from. So people will not know the information itself. They'll just know like, oh, they're getting information from somewhere, which is like not a big deal. Okay, next is timestamp dependence. This is very similar to what we said with the, I don't know, what was it? Yeah, force feeding. Very similar to what we talked about with force feeding. Basically, contract, again, depending on some sort of on-chain thing for a check. In this case, it's the block timestamp. So an example of how this could be used is maybe there's some sort of auction contract, and it relies on the block timestamp to end the auction. If a validator were to bet on in this auction, right, so like let's say they put up their price, and then they could choose to immediately propose the block after they put up their bid. I guess it's a bid. After they put up their bid, they could immediately propose the block, which would prevent other people from bidding, right? That would end the auction. But maybe it wasn't supposed to end at that time. They ended it prematurely because they have the ability to do that. So what this does is it gives validators an unfair advantage sometimes. And ways you should get around this is you want to use an external time source. You don't want to use the time of the contract or the timestamp of the contract as a check for stuff for this reason. And it's important to keep in mind, it really only is like 15 seconds that they can really play with, right? Like it's not like they have an hour and a half to mess up your contract. It's like 15 seconds. But still, you want to prevent your contract from being able to be messed with in that short time difference. So maybe just don't make it so time sensitive that it's down to the second. In case you were wondering, these is OWASP top 10 smart contract vulnerabilities. I think we went over all this and also some extra ones. So just like FYI. Really quick, and I promise I will stop talking. How to secure Web3. What can you do? So some things you can do if you were trying to secure like a smart contract. First thing you should do, code review. You want to look over the code, see if there's any errors. It's like very obvious, right? Other things you can do, there are smart contract auditing tools. So just like any other like application or whatever that you have like SaaS tools for, you can have like a static analysis tool for your smart contract. There's also other ones that do other things. Testnets are like fake blockchains where you can test out your code. It has like fake money. So you can post your smart contract on a testnet and make sure it works correctly, and also definitely test edge cases, just to make sure everything's running correctly before you put it on the actual blockchain. Once it's on the blockchain, it's there forever. So like measure twice, cut once, right? Pen test, you can pen test smart contracts. You can use your testnet for this. You're just trying to attack it in like ways we talked about, maybe other ways, and then see what happens, if anything. And then there's also consultants. So there are smart contract auditing and pen testing companies out there. If for some reason like your company had a smart contract and they really like needed help with this, you could just hire someone else to do it and not learn it at all yourself. That's fine too. And then some next steps. So if you wanted to get into this, what should you learn? First of all, the coding languages. So you want to maybe you want to learn Solidity, maybe you want to learn Viper, maybe you already know Rust, so you're like a step ahead. That'd be cool. Blockchain infrastructure. I didn't explain that much of this, honestly, and I know very little compared to other people, so imagine how little contextualization was really given in this presentation. And then also, like, web app security is important. A lot of the concepts kind of carry over, like we talked about with all the familiar vulnerabilities. And then also, like, if your smart contract does have a front end, you should make sure that's secure too. This is like my last thing, I promise, I think. Yeah, it is. So there is one class here that you can take about cryptocurrency, and it's this. Guys, when I took it, it was a seminar, but I think this is the correct course code. I tried to look it up. What? Okay. Fine. Devin says you can take Finance 1 to learn about the blockchain. Oh, I don't know what he's saying. Okay. It what? Okay, it's back to a seminar. I don't know. It's always called this. Cryptocurrency Blockchain Analytics. You can try to find it. It counts as a credit for something here. I will say things you'll get a lot of exposure to is you'll learn a lot about like Bitcoin. We talk a lot about Bitcoin. It is a lot of like blockchain analytics is different. We do like digital forensic side of it, so it's a lot of like tracking transactions on the blockchain. What you're not going to get to do is you're definitely not going to touch a smart contract. You're probably not going to talk that much about Ethereum, honestly. It was like a lot about Bitcoin. But if you're interested, this is kind of your only option, so consider it. Also, you want to learn more about blockchain technology. YouTube is a great source, but when I say blockchain technology, I mean like learn about how proof of work works. I don't mean watch a get-rich-quick scheme online and then try it, right? So those are different things. And then if you need resources for coding, this website I have there it lets you like code in Solidity. It tells you how much gas your code uses, and you can try to like run it. Oh, that's another thing. You know how like all the CS classes tell you about time complexity, right? And you're like, oh, I don't need to know this. This is stupid. Well, on the blockchain, actually, the more complex, the more it costs you to run. So you probably do actually want to know, what makes it the simplest to run. And then just last thing, there's some resources there is the OWASP top 10. And then the second one is like pen testing, try it yourself, smart contract stuff. So yeah, and then that's it. Are there any questions? Did anyone have a question? No? Okay. Cool.
All right. Demos are all up on flags.ritsec.club. Go there, make an account, get started on them. They're pretty much just like surrounding, like analyzing Web3 crypto wallets. So go and check that out. Find some flags. Good luck.
Hello. Sign into the meeting and then you can get pizza. Sorry it was a little late, but power outages tend to do that. Sign in. I need it. Please. Hello. I got a skull ring. I don't know what size, but if any of your friends are missing a skull ring that was out by pizza, it's on my finger.
Hello. Hello, hello.
It is time for security news. Woo! Yeah, you can clap. That's okay. There we go. Go back. I don't want that. Give me 1 second. Okay, now it's time for security news. Here we go. Security news. Fuck. There we go. Are you interested in presenting? Sign up to present at presentations.ritsec.club. We have the blog. VRigs posts a lot of stuff on there. That's pretty cool. If you're interested in reversing and things like that, go check out the things on the blog. If you want to post anything on the blog, you get points. You get reward points to redeem different prizes. So make sure to check that out. Contact me or Daniel LaChance, the president, through Discord. Make sure to sign in. Signing in is important because it gives you pizza and things like that. So join the Discord if you haven't already. There's a QR code. Check the calendar. I updated it. Former Red Team Recruiting IG is now Offensive Security IG. The time for that has been changed, and it is reflected in the calendar as well. So, RITSEC mailing list. I send out emails from time to time. I sent one out on Wednesday detailing stuff that's coming up and stuff that will be announced. So, follow our social media. Clap up for the sponsors, please. And Finn. Announcements. Going to run through these because we already did these basically. Mentee signups. If you want to be a mentee to someone's mentorship group, sign up here. Scan one of these QR codes. It's really informative. You learn a lot. So, CTF Black Team applications. I signed up. You should too. We need challenge authors and people to do cool stuff. So please join. ISTS White Team. This is very important. ISTS or the White Team is like the backbone of actual comp day. We need tons of White Team members, so make sure to sign up. No, finally, cybersecurity news. What do we have? We have a China-linked UAT 8090, targets IIS servers in Asia, and the Trump administration rescinds Biden-era SBOM secure software attestation guidance. What do you know? So first off, this news is hot off the press. This came out this morning. Don't ask how this news came out today. Don't think about it too hard, okay? Meaning, I did this morning. But, all right, here's a high-level overview of the incident and the things that happened. If you're interested in learning more, I have the link to the actual article, or you could just look it up yourself. So, cybersecurity researchers have discovered a new campaign attributed to China-linked threat actor known as UAT-8099. That took place between late 2025, like October, I think it was, and early 2026, so now. The activity discovered by Cisco Talos, I think that's how you say that, which is the Threat Intelligence Security Team part of Cisco, has been targeting vulnerable Internet Information Services, so IIS, that's what IIS means. Servers located across Asia, but there's a specific focus on targets in Thailand and Vietnam. So UAT 8099, quote, uses web shells and PowerShell to execute scripts and deploy the go-to HTTP tool, granting the threat actor remote access to vulnerable IIS servers. So this was first documented in 2025. And they were trying to facilitate search engine optimization fraud. But the most recent campaign, the one I'm talking about here, is often using web shells, soft ether VPN, and easy tier to control compromised IIS servers. So how was this campaign different from other campaigns? Because I just mentioned there were multiple. Well, interestingly enough, The threat actors in this campaign started to use red team strategies. Can you get the people outside to like close the doors or like stop talking? Thank you, Luke. Where is I? Yeah, the threat actors in this incident started to use red team strategies and legitimate tools to evade detection and maintain persistence, which is a big thing. So if you're interested in red teaming and some of those practices and like what that's like in real life, focus up because here's the rundown. So the attack chain started by gaining initial access to an IIS server, either by exploiting a known vulnerability or through weak security configurations in the web server's file upload. This enables the threat actors to do a couple things, like executing reconnaissance commands to gather system info, to deploy VPN tools, and establish persistence through the creation of hidden user accounts. And they did a couple of things like deploying open source tools like Sharp4 remove log, which removes Windows event logs, OpenArc64, which is an open source anti-rootkit, and as I mentioned before, go to HTTP, which is a remote control server type thing, akin to a C2. And lastly, the main part was deploying bad IIS malware. So what is the end goal here with this? Well, this malware scans incoming requests to IIS servers to check if the visitor is a search engine crawler. And if that's the case, the crawler is redirected to an SEO fraud site. Remember, SEO is search engine optimization. However, if this request is from a regular user and the accept language header in the request indicates Thai language, it injects HTML containing a malicious JavaScript, redirect into the response. So basically, in a nutshell, they're trying to do SEO poisoning to manipulate the search engine algorithms to promote malicious websites. So some cheeky stuff. On to the next one. I'll go over this one a little quicker because I don't want to do too much security news. I have to change this. There you go. Oh, that's not what there you go. Shocker, the White House did something that might not be good. In their eternal wisdom, they issued a memorandum, I think that's how you pronounce that, not sure, to roll back software security requirements established by the previous administration. And some of these requirements are included like following NIST suggestions to use SBOMs, which are software bills of material, and quick tangent. A software bill of material is a list detailing libraries, modules, and other dependencies that are used to build a software application. So Office of Management and Budget Director Russell Vaught issued M-26-05, which rescinded the past two memorandums, which were, their purpose was to require federal agencies to ask for like a self-verified document from commercial software producers that guarantee that the contracted software meets NIST security development guidelines. And the other one, M-23-16, just kind of built off of the previous one. Vaught claimed that, quote, they imposed unproven and burdensome software accounting processes that prioritized compliance over genuine security investments, and added this policy diverted agencies from developing tailored assurance requirements for software and neglected to account for threats posed by insecure hardware. So, a lack of SBOM can be bad because these are basically a list of all the softwares and dependencies used in this application. And, all it takes is one vulnerability in something to have consequences on the supply chain. So it's really important to have these lists of what things are and how they come together to do shit. Yeah. According to Jeff Williams, co-founder and CTO of Contrast Security, as well as a founder of OWASP, so industry professional says that this rollback is a, quote, disaster due to the loss of radical transparency. Williams says this rollback sets us back to square zero and that agencies are now free to do whatever they want to ensure their code is secure and nobody has to attest to anything. This is just one opinion, though. many people are divided, many security experts are divided on the actual consequences of this, mainly long-term consequences. So I advise you to look up this story and make your own informed decision on the issue. Here are my notes. That's all I have for you today. So now we have Tanush and Alexi with Fuzzing Boot Camp. Clap it up for them. Perfect. Here we go.
Oh, hello. This is Fuzzing Bootcamp by VRIG. I'm Alexi. I'm a third year, and I'm the lead of VRIG, and this is...
It's Tanush, another lead of VRIG, and we're going over fuzzing.
So this is just kind of like the agenda for today. I'm not really going to go over it, but yeah, I don't know. I don't think it's that important, right? Yeah, it's just the agenda. Okay, so what is fuzzing? Or I guess what is the point of fuzzing? The point of fuzzing is to find otherwise impossible, quote unquote impossible to find bugs by basically just throwing like random or semi-random input at a program and waiting for a crash. Or I guess maybe hoping as well. Basically, you typically test anywhere from like thousands to millions of cases or inputs. And in like low level, for some background in like low level languages such as C, a crash usually like indicates that there's some sort of, or a crash will indicate that there's some sort of like memory corruption, which is potentially exploitable and interesting. AFL plus, or I guess on the second point here, American Fuzzy Lop, or AFL, has been the biggest innovation in like low level bug finding in recent years. When did it come out? 2013? So it's been a while, yeah. There's been a lot of improvements on top of it, but this is kind of just like a big, massive jump forward, or it was, yeah. So before AFL, fuzzers were kind of, or they were often like quote unquote dumb, and just threw random input or data like at a wall. So imagine you had like some sort of command line tool, and you were just like echoing input like directly into it. That's basically what they were doing. AFL, on the other hand, is smart because of genetic algorithms. Essentially, AFL++ will mutate on and keep inputs that find new code paths or increase coverage. And that allows it to basically just like drill through like a program to find interesting code paths and exploit, or bugs, I guess. Yeah. So on the left here, there's like you have this diagram or little code snippet here. This is kind of or I guess it kind of shows like a big a problem here called like the nested problem, where like if we look at it, like I mentioned that previously, or the dumb fuzzer before AFL would have to guess or has a like 1 in 256 to the 5th chance of hitting that case 5, because it needs 5 consecutive like chars all in the correct order, and each char can have like 256 bits, so you get 256 to the 5th chance of guessing the input. That's never going to happen. So what coverage analysis does is that it will notice when the input starts with 1, so in that first if statement, and when it reaches that part of the code, it will save that input and then mutate off of it because it reached into a further path, into a further code path. Okay, I think that's everything on there. All right, this is kind of just like a bunch of, I guess, like industry fuzzers, right? Or popular fuzzers. AFL++, like I mentioned, is kind of like the industry, oh, this is weird, industry standard. Yeah, and libfl is also pretty good. It allows you to like build your own custom fuzzers. And this could be maybe more interesting if you were fuzzing like some non-standard targets, maybe like such as a kernel or embedded devices. Yeah, and then if you want to look at this on your own time, feel free. I don't think it's too important though for the rest of this. Okay, cool. So on here, we just kind of have a performance summary of for when a bunch of these fuzzers were fuzzing libpcap, which is a just like a packet capture library. And we can see that on the left here, AFL++ and Centipede, they had both over 3,000 or median branch coverage, so they perform the best. And then we see a big drop off here with Eclipser to AFL last. I don't know why that is. Are those real?
I think just mutation strategies aren't
Okay.
for it.
Okay, that's fair. Cool. And then we'll move on. There's nothing. It's not too important. Oh, was this on here?
Yeah.
Not on the. Did you? Hold up.
Oh, it's like a slide transition.
Oh, is it?
Yeah.
I didn't even see that. Okay. Cool. Whatever. My bad. Cool. So let's go over coverage-guided mutations. Essentially, coverage-guided mutations make modern fuzzers such as AFL++. It's how they are so effective. The fuzzers will learn which inputs are valuable, and then based on code paths that those inputs trigger. So the goal for this is to basically reach every one of these basic blocks on the image on the left here. Some background: a basic block is basically just like a straight sequence of code without any branching, so like no jumps or calls. So this would be like one basic block, you get another one here, and then you get like one here. These are all basic blocks. So basically your goal is to reach every single one of those basic blocks. The way it does this is that it will keep track of which edges or basic blocks of this graph have already been visited, and then if a new input hits in like unseen part of the graph, then that input is considered interesting because it reached a further part of the code base. Okay, so in the orange here, it's kind of highlighted. Describe it basically just like describes the logic for if AFL++ finds an interesting program, what it'll do when it saves it. So it calls a save if interesting, which we'll call like calculate new bits if necessary. That which will compare like the current execution path against like a global map of all the paths found so far. My bad. And then it'll look if it has any new bits, and if it does, then it will save that program to the input queue or the corpus. If it doesn't, it'll just continue. And then a bit tangentially, discover word is also there. Basically, the point of that is that fuzzers will often struggle to like get past like quote unquote like magic values or like hard-coded strings. So for example, if you had like a get or like a post somewhere in your binary or just some like random digit, it's not going to be easy for the fuzzer to discover those or get past, know the correct input to get past. So basically, discover word will look for interesting like byte sequences in the interesting input, and if it finds like a potential word or like a sequence of bytes that's like a single unit, it will save it to like a dynamic dictionary from which like future mutations can splice these discovered words into like other inputs to hopefully mediate or alleviate that problem in the future. Mutation strategies, I think they're at the middle here. They're just ways that a fuzzer can basically modify or mutate a given input. And fuzz level, another thing, is basically the number of times AFL++ has cycled through its input queue or corpus. Every single time it cycles, it will increase the havoc stage. And then when that gets incremented, actually, I'm not too sure. when it that will I guess the havoc stage, sorry, will determine or it'll eventually cause the fuzzer to perform like many random or like high energy mutations all at once in hopes of trying to like find new edges. Do you want to add? Do you know when they're like when it's triggered actually? Is it just on every increment? I'm not too sure.
It's dependent. It's fine. It
Okay.
depends on the expiration point.
Yeah. Okay. Cool. So here we have like three kind of main fuzzing modes. Excuse me. Standard function, like I mentioned earlier, basically you're just feeding raw data into a program. This is very slow because I/O and OS overhead, and starting and stopping a process thousands of times is not efficient. It's like rebooting your computer every time you want to like open a browser tab, for example. So the next improvement is forked server. Instead of restarting the program every single time, you use a fork server. Basically, you start the program once, you let it reach the entry point, and then you clone or fork the process in memory for new test cases. This is better because it skips like expensive overhead of like initialization and like loading libraries, for example. But it requires like the binaries to be instrumented, which is what the AFL Clang LTO and AFL Clang Fast are in the ++. And then finally, we have persistent mode, which is, I guess, arguably the best. It'll basically stop treating the program like a command line tool, so there's no more I/O. And instead, a harness will feed data directly into like a specific function or part of the binary that you want, without stopping the process. At least until a certain number of iterations have happened. So you have no more forking or restarting, so speeds can reach tens of thousands execs per second. It's a bit like wrong. You still fork, but not as often, or like barely. Yeah. Cool. Fuzzing entry. Hold on, let me try. I'm a monster. All right, cool. libfuzzer. This is an example right here, and then the next slide as well will be two examples of just persistent, persistent like fuzzing modes for libfuzzer, and then the next slide is AFL++. Libfuzzer was on the previous slide, and it's an in-process coverage-guided fuzzer. So, like I mentioned, like traditionally, a fuzzer has to fork and exec a new process for every single test case or input. However, this example and the next one show persistent mode. Yeah, okay. Basically, persistent mode will just keep the program alive and then feed new data in a loop. I think that's a bit more obvious on the next slide as well. Cool. So you kind of have like two main functions here. You have your LLVM fuzzer test1 input, which is just the fuzz target or the function that the fuzzer is going to call repeatedly. And you have your data. It takes basically two inputs in the signature. You have your data, which contains like the mutated input generated by the fuzzer. As a note, it'll like always return 0 or -1. The other values are just like reserved. And you have libfuzzer, or I guess, yeah, like I mentioned, libfuzzer will always look for this specific signature for LLVM test one input. And yeah, that's like required. You also have like LLVM fuzzer initialized. This is optional, and it just allows you to initialize like functions, or it's an initialization function that runs once when the fuzzer starts. So this could be useful for maybe you want to like load like a large like database into memory or set up some global states. You can do that there. On the document or on the docs, it was recommending not to do it unless you need access to argv or argc, but I don't know, probably not that deep. Yeah. All right. I think this is a better example in my opinion, just because it shows like the actual loop. But this is persistent mode for AFL++. Yeah, so I think the most important thing to take away from this is like all of the macros. So what we can see here is you have this AFL init, which will basically just like act as a checkpoint. So it'll tell the fuzzer like everything before this is like a one-time setup, and then to start like the actual cloning process here. So it doesn't have to clone. Well, it won't, I guess also, yeah, it won't clone on every iteration. I will get to that. We also have AFL fuzz test case buff, which will it's just a pointer to a shared memory region. So instead of reading from a file, AFL++ will like write test cases, and like I guess the program will read them from that shared memory region. And yeah. And then we actually have our main loop here in the while with the AFL loop. This is like the main loop. So every single time it loops, the fuzzer will like, I guess quote unquote like reset the program. It doesn't really. It'll just basically loop through it'll have one process and then just keep looping and calling this like LLVM fuzzer test one input int max times. And then once it reaches int max times, it'll refork. It does this so because like after maybe you have like a million iterations or however many int maxes, that's a lot. You'll probably inevitably have like memory leaks, even if your harness is written well. So it just like takes a preventative step to try and alleviate like false crashes. And then AFL fuzz test case length, which is like the test of the length of your input, and LLVM fuzzer test one input is, like I mentioned, like the target function or what you're actually testing. Here we also like used like the function signature from libfuzzer, which is like just like good practice. And then one more thing I wanted to note is like the argc and like the argv up top. It's not really important, but they just like suppress compiler warnings. I just thought it was interesting. Okay, I think that's everything on there. All right, cool. Writing good harnesses. This is very important. Let's just go over each one. So for the first one, you want to fuzz areas where the program takes in raw input or unstructured input, as this is where your program handles like untrusted like data. So think about like a network protocol parser, for example. By using like a coverage guided fuzzer and starting at like the top of the code flow, you can you'll basically just allow your fuzzer to discover interesting inputs and code paths. Cool. Also, depth versus breadth is pretty important. Universal harnesses are slow and like often get stuck in like shallow code paths. So creating small like focus harnesses allows you to reach better execs per second and like drill deeper into like your target code path. Then you also have cleaning up the programs, or I guess cleaning up the program's global state helps ensure that when the fuzzer reports a crash, it isn't just the harness crashing, but it's an actual legit bug. So over potentially like millions of iterations, memory leaks will cause your fuzzer to crash and report false positives. So cleaning up the global state will help alleviate that, like I mentioned. I think this is only really necessary if you have like a global state as well, because ideally your like LLVM fuzzer test one input is like stateless, and that way it doesn't rely on any like external data. So it makes like the managing the states easier. And then one more thing, like using LLVM fuzzer initialize to handle heavier tedious initialization steps that don't need to happen for every single execution. And then this will also just keep your fuzzer like fast and efficient. So I guess it's also like, just good practice. We have some more here. Basically, also, by not allowing your fuzzer, or not allowing for, basically you don't want to reuse multiple pieces of data, or the same piece of data as multiple parts of the data flow. And by not reusing a piece of data, or a piece of fuzzing data to be used as multiple parts of the data flow, you prevent like collateral constraints. I don't really know. Kind of AI slop, honestly, I'm not gonna lie. But imagine like a byte gets like used to identify, let's say like the length field, but it also gets used to identify like a type. Maybe there's like a type field as well. If the fuzzer mutates on that like single byte, then the length field might get like, or I guess if it mutates on that single byte to modify or mutate the type field, it'll end up breaking the length logic and prevent the fuzzer from reaching deeper code paths. And then also, each piece of fuzz data should map to one specific test scenario. I think it's a duplicate for number 2 here. It's just saying again, like clean up your global state to like help alleviate false positives and obviate real bugs as well. Okay, cool. And then debug output can significantly slow down your fuzzing. So remove like all debug statements basically when you actually want to do your campaign. Another thing is don't let your fuzzer waste time on garbage inputs that you already know will fail. So maybe there's like an input or maybe your input is 0 bytes, but you know your target always requires at least 4. So instead, it helps to obviously like have good seeds or initial inputs, but you can also validate your inputs in a way that helps you reach your target code paths. Cool. Summarize your code. Okay. And then the last thing here, you just basically want to optimize your source code for your fuzzing environment. There's kind of like 2 main ways you can do this, is like stubbing out just a relevant code and like creating mock functions that return hard-coded results. For example, like if you wanted to like stub out some like math or like hashing algorithms when fuzzing like a parser, because you know those like algorithms or the math logic is just like irrelevant for the parser logic. Yeah. Almost through here. Is it? Oh, it is on the right. Is it? Oh, it is. Okay. My bad. Here, basically, this is like just for like when you're like compiling your binaries in the fuzzer. You have kind of 3 different instrumentation levels with AFL++. AFL Clang LTO and AFL Clang LTO++. This is the fastest, or like the gold standard. It performs link time optimization, which will essentially just result in like slightly faster binaries that produce better coverage. And then we also have like AFL Clang Fast and Clang Fast++. These are still very fast, but and use a compiler plugin to instrument the binary. And then we have AFL GCC Fast and G++ Fast, and these are a good fallback for older systems or specific GCC like dependent projects. And then cool. And we'll go over environment variables, or sorry, environment flags, basically just like sanitizers. So while like the fuzzer might trigger a bug, if the program doesn't like actually crash in a way that the fuzzer notices, then the bug is missed. So sanitizers will instrument your code at compile time to detect bugs and vulnerabilities during runtime. They act as basically just like guardrails, watching your program execute and like catching problems that might normally be silent. So maybe for some reason you went out of bounds in an array, but it didn't actually like really do anything harmful and your program doesn't crash. If your program doesn't crash, then the fuzzer's not gonna know that there's like a potential bug there. So that's where sanitizers come in. Essentially, they just add checks. For example, like around like a memory load or store to achieve this. And then, yeah, these are just also just, if you go back, I was just gonna mention, these are just kind of more for your reference. They're all like pretty cool and interesting, but I don't know. If you want to look at it on your own time, I think it's more efficient. And we have 2 more AFL. What do I have here? AFL TSAN and LSAN. I think libfuzzer has both of these enabled by default, and it's also important to note that some of these sanitizers like cannot be used together. For example, ASAN and MSAN, you can't use them together. So just like keeping that in mind is also helpful. Also, the sanitizers tend to like slow down the fuzzer quite dramatically. So you might want to be like strategic with which ones you choose. And then finally, we have, or at least for this slide, we have input compiler avoidance tag. Basically, it's just like a macro. This like if, fuzzing build mode unsafe for production. This will basically just tell the fuzzer to not spend any time exploring like whatever is in those or like a certain code path. So imagine like if the code logic is checking like an HMAC or a digital signature that the fuzzer like will never be able to guess, then you can just kind of use this to always return like a valid signature. Yeah, you can basically just eliminate the need for the fuzzer to guess the correct checksum. Yeah, I think you also just like wrap your code in the if def and end if to achieve that. What? I don't think I have time. Oh. Maybe if we have time, we'll come back to the demos, but I think we're just going to skip them for now. And then, all right, cool. Tanush.
Yeah. Okay. So the other part of this, one of the next interesting things that we want to talk about is the concept of making custom fuzzers and improving what a standard fuzzer does, right? So obviously programs are really complicated, and if you have a program that takes in like network traffic, like most of the time random bit mutations and bit operations aren't necessarily going to result in meaningful inputs. And let's say you kind of know the structure of your input style, or you have tags that you know, and you know the format of stuff, you can pre-make your fuzz input to actually be standardized to that input. And one of the systems for this is libafl. So libafl is a library for building custom fuzzers. It's made by the same team as AFL++. The main difference is it's in Rust, and now you're writing your fuzzer as well as then you have to write your own harnesses as well. So it's 2 layers, and it's kind of important to remember like the difference between these 2 layers. That'll come up in some time. But libafl has a bunch of powerful extensions and additions that make it very useful when you're fuzzing complicated targets. And I think it's important to also talk about selection process. So when you want to use AFL++ versus libafl, if you're trying to target a code base that's very highly audited and well tested, it's worth trying to create custom fuzzers and try to perform some level of optimization and innovation in terms of what the fuzzer's doing. So this section was like really heavy code analysis and kind of code explaining. We'll do it, but yeah, definitely worth looking to on your own. It's important to remember this is all in the context of writing your own fuzzers, and fuzzers are pretty complicated. So yeah. First of all, error handling and has metadata. So it's useful to actually keep track of error handling, because sometimes systems might crash in different ways, and some errors might actually be interesting, and you might want to track stuff if it does error out in certain ways. So that's why you're given these primitives. Has metadata, again, you might want to rewrite the entire metadata format for what you're keeping track of, right? An example of this is somebody wrote a fuzzer for a video game where they tried to fuzz the character movement. And again, it's genetic algorithms, genetic mutation. So the strategy here is after your character moves to an X or Y, Z point, you might want to keep additional metadata on the movement of the character throughout the map or something like that. So again, the idea here is that you're given so much control, you can do some very interesting things. Corpus. So corpus is where your test inputs are stored, and this is obviously like kind of the peanut butter and the PBJ sandwich, where it's like this is like really the most important aspect of your fuzzer in terms of this is what gets you the bugs, right? What this allows you to do is you can do things such as like maybe writing to a database is something we actually did. Not with libafl, but just something we did, is we start storing all of our test cases into a Postgres database, and that's just something you can do. It's just like changing where data is stored, how it's stored, how it's scheduled. Maybe you don't want to test all of your corpus inputs at once, or you want to schedule it in different ways. This allows you to do that. Yeah, let's go on to executors. So executors are kind of the idea of your LLVM fuzzer test input 1. This is how, in terms of the actual fuzzer, when you're building your own library or your own fuzzer, right? How the library sees it is it's seen as like a singular input. So there are different types of executors as well. And we kind of talked about that, right? The in-process executor, fork server, executor, in-process, fork executor. The main idea here, right, is you're allowed to define what is the start and end of an execution. So in-process executor, right, we're talking about the idea of, okay, we're going to keep spawning grandchild processes every single time after, say, 1,000 loops of the same input, right? Fork server, the idea is, okay, every time we have a new corpus, a new input case, test case, we want to fork the grandchild, and we want to keep all of this in the parent children processes shared memory region. And what you're allowed to do with executors now is you're able to essentially redefine what execution looks like, and you can create something like a fuzzer for a custom kernel or an operating system where your execution is actually starting QEMU and maybe tracking the QEMU states. And after QEMU finishes, you look at the inputs from the registers in QEMU and whatever, right? And executors essentially allow you to completely redefine what a process does, or the end to end of a process execution or test case. Breaking down generic process executors. The idea here is we have our harness. This is the function we actually are going to execute. Points to that, and then we're going to keep track of our execution counter. There are several global states and values that we care about. The most important things are pre-execution hooks, call to your target, post-execution, and cleanup of global states. This is important because you're able to now define, say you want to do something before you execute a function, you're able to now create your own hooks to that, and maybe this is something on the, before you run, what's a good example? Let's say you want to store some level of metadata before you're going to execute a function, right, on a process or a server, right? Let's say you're fuzzing a custom server, it's written in C, and you want to save actually the inputs or what's stored on the website of the server. Let's say it's for like a IoT embedded router or whatever. And every time before you actually execute your target function, which is your harness function, right, you actually want to see what's on the website for whatever reason, right? You're able to do that. And then let's say you want to compare what's not on, or what's on the website after that execution. You can do that in your post-execution hooks. And I don't know, let's say you want to clean something up. You also have the ability to do that with your clean global states. Yeah. Execution in librs. Okay. This kind of is how you're going to handle providing input to your harness. So you have your target, you have your buffer, and then your global variable libfuzzer test input 1. So this is going to actually send data, to your harness, get back to you, and then you're going to have your states, your instances, the event manager, the execution timeout. So all of this is like the result of that execution, and it's your executor, and you can continue to run the executor as indefinitely, obviously, as it goes with fuzzers. But the idea here is if you want to, say, change the format of the input buffer, right? This is kind of where the lines between a custom fuzzer and a harness sometimes get blurred, where your harness allows you to take in your input buffer and clean it up and maybe define it into some custom structure. And, it's still garbage data in some ways, but you're now redefining it into a custom format. What you're able to do in the execution and the data here is you're now able to redefine the actual buff before it goes into your harness, where it might already follow a predefined format. So let's say you're going to be fuzzing ELF headers, and you don't need, ELF files. You're fuzzing just ELF files universally. Let's say you want to always have like your ELF header format, and that's just something you can tack on to the very start of every buff. Yeah. Mutators. So mutators are a pretty important and interesting idea when it comes to fuzzing, because what mutators allow you to do is essentially define how you're going to mutate things and what mutation looks like. And I think we talk about this a little later, but we'll talk about some custom mutation strategies and mutators that exist that let you fuzz grammars. So if you've ever seen like a programming language, there's obviously like a definition for what the program language grammar is. So obviously every language and every program can be defined in some sort of like general abstraction, right? English, right? We always have a subject and a predicate, right? Subject and predicate. Okay, I'm pretty sure that's right, right? Subject and predicate. You always need those two things, and that's just like a format of an abstraction, right? Of a grammar. What can a subject be? Obviously, a shit ton of things. A human being, a name, a location, and a predicate can be all sorts of things as well, right? But the main idea is that you have this predefined grammar, and that's just a form of mutation. Let's say you want to mutate around those grammars instead of just arbitrary havoc mutations. And havoc, again, is just like bitwise, bit level mutations on the actual input buffer. But yeah, I don't know. This isn't that important to this talk, honestly. This is like more important if you're like really trying to get into the weeds of the internals for your fuzzer, but it's fine. Yeah, okay. Mutators in example code. Honestly, kind of explain this. This is fine as well. A lot of this has been shifted and stolen from a VRig talk that we did a while back. But yeah, so we can kind of see here in this example where in the actual source code of libafl this is actually happening, and this is kind of like helpful just to understand, I guess, the internals of the system. If it's confusing, you're also right, because you're writing the library in Rust, but your harness or your fuzzers are also in Rust. So 2 forms of Rust before you can actually do anything, I guess. But here we kind of see where our mutation happens, and what this allows you to do is change the mutator at like very low level if you want, right? If you want to make the mutator as custom as possible, where you're only mutating like certain tags, right? Let's say you have a list of like 100 tags that you know will exist. You can arbitrarily mutate on those if you want, and you can redefine mutator selection in this section of the code. Yeah, this is in librs. So, we also had a demo for this. We're just not gonna do that. Yeah, so grammar and structure aware fuzzing. I kind of talked about this, and let's, I guess, talk about grammars for a second because they're kind of important, and some people might not fully understand how grammars work. The idea with the grammar, right, is you're abstractly defining what something can expand to, is the best way of putting it. So you have your start, and then that points to an expression. Well, what is an expression in math? Well, it's a term plus another possible expression. Okay, we already defined what an expression is. It's a term plus an expression. Okay, sure. What are term? A term, it can be a factor. A factor can be an integer can be a digit, and you have, say, 6 digits. Right? Or you have like a set constrained number of digits. In this case, they're actually just hard coding the digit to 6. But the idea here is we can define all the possible formats in a grammar. So let's say digit, right? Digit can equal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or not 10, but 9. But yeah, so those are all of the possible values for your grammar. And when you're generating the definition of a language, your goal is to essentially describe all of the possible combinations for some kind of language or protocol. For example, something that I had to unfortunately read the grammar for was like the baseband custom dynamic or vector imaging system. So if you didn't know, and you probably shouldn't know, baseband towers actually have a custom dead imaging format, and just this is honestly tangential. Who gives a shit? It's such a tangent. I'm sorry, but the idea is that like you have grammars, and they allow you to define any language, and this kind of explains it. Kind of see the idea here is that you can keep defining terms, and you can combine terms, and you can generate all of the possible values. Why do we actually care about anything I just said? And it's not just like an insane man's yapping. The main reason is there is something called Nautilus grammar mutator. It's inbuilt into libafl, and the idea here is you can define your own custom grammars for something like, say, XML. And obviously, there's a lot of XML parsers, and XML parsers written in C might be bad because they can lead to bugs. A common trend in security research and vulnerabilities is that a lot of parsers are like pretty big no-nos because they're complicated, they're hard, and when you're parsing things that are like really complicated, like XML is not even that bad, but think of if you're like parsing like a programming language, there's non-trivial chance that there might be a bug in your custom parser. So something that's really useful for finding bugs is grammar fuzzing. And you are essentially, as you can see in kind of the image here, we're like making a custom grammar for XML. So we define our start, which is our document, and then XML and then document. And then we define what XML content can be, which is XML and then maybe more XML content. And then we define XML content as empty as well. And then we go ahead and define possible values for XML. So tag, adder, and maybe XML content again. And we kind of keep going down until we define a bunch of rules, and then we can keep adding things. And there's nice things in this library like regex. So if you want to define what the regex format for a specific grammar value is, you can do that. The main value here is you have syntactically correct inputs, which is like important if you're fuzzing like a programming language. And you might find better mistakes in the parser, but more than that, when you have a guarantee of syntactically correct inputs, you no longer need to, you can go past the input validation that formatting does, right? So if you're trying to fuzz a programming language, obviously the first thing that happens in any programming language or any compiler is it tries to validate that your syntax is correct, right? And if you have broken syntax, the code doesn't even compile. So that's not that useful a lot of times when you're fuzzing complicated targets like JS, JavaScript. And you actually want to guarantee syntactically correct inputs as best as possible. So grammar mutations are really useful for stuff like that. Yeah. So protobuf-based mutations is kind of adjacent idea, and that's when you're like when you want to fuzz, say, a protocol, and you know like the general format of a protocol, and you want to mutate the objects in a specific protocol and not just like arbitrary inputs. It's really useful for generating, say, like here you see like message.proto, and you define what the message can be, and then you get to serialize that message to a string, parse from that string, and then you can send it out either into the fuzzer input or, technically protobufs are used for a lot of things, but yeah. Snapshot fuzzing. This is kind of, okay. You can like go over these two things really quick. This is like another form of really advanced fuzzing, and we were kind of talking at it at the start when we were talking about writing our own custom executors. So the idea is that you're essentially now writing an executor to create a snapshot of a virtual machine. The executor, like, yeah, when you take a snapshot of a virtual machine, it's the same idea here. You're just going to take a snapshot of it before you start inputting values. And then as you input values, you're going to keep track of like the VM's internal registers and what it's doing and how it's doing. And you care about what the virtual machine state's like. And whenever it finds something interesting, you then save that new snapshot. And then maybe you do new mutations around that. And as you can see, it allows you to play literally Mario. You can fuzz Mario into existence and play the entire game of Mario by trying to calculate all the states. And you can define what, a new interesting value is. And in this case, it's Mario moving forward and not dying, right? This isn't perfect. There are issues with this, but it's a really efficient system for fuzzing complicated targets in two ways. You want to fuzz the Windows kernel, which is kind of black box, as well as Windows black box binaries. That allows you to fuzz targets like that, as well as allows you to, say, fuzz a network service where you redefine the entire Linux kernel's network stack. So now it takes input from your custom fuzzer, which allows you to directly send inputs through the Linux kernel, and now you avoid having to write a harness, really, and you can just use Nixnet and kind of win. Finally, we have like Frida fuzzing. Okay, this is like a tangent one, but whatever. Frida fuzzing is like the concept that, hey, you have a Windows standalone binary, and you want to hook into, say, the starting of the Windows binary and execute that. And essentially, Frida is a tool that allows you to do this by dynamic analysis. And Frida is a really cool tool, and you can look into it. And there's a bunch there in terms of like shadow memory and keeping track of everything. But the main thing with Frida is it allows you to dynamically track and trace every binary. It's really good at it. And what this also means, it allows you to trace and track basic blocks, because it actually itself works on the basic block level. And so every time you get to a new basic block or you reach a new edge in your code coverage, you now can save that. And, same idea where you're now using that information to fuzz and send inputs using Frida itself as well. So twofold value with Frida. But yeah, all of this is kind of just built up to what our work was for the last like 3-4 months, where we got really into the weeds of a JavaScript compiler fuzzer called Fuzzily. And yeah, I'll let Alexi take over for this bit.
All right. Just gonna kind of go over a high-level overview of the main points of what Fuzzily is and kind of like what it does. So I guess Fuzzily's like main goal is just generating interesting JavaScript code. However, because Fuzzily is targeting like core interpreter bugs, so think like on your browser you have something is running your JavaScript code on your browser. You're targeting that engine, for example, and that could be like a JIT compiler. But doing so, it faces two kind of core problems. So you want to ensure these. You want to ensure. Sorry, what? Oh, sorry. You want to ensure syntactic correctness, and you also want to ensure semantic correctness. So syntactic correctness is just making sure that your JavaScript code that you generate is actually syntactically valid. The way Fuzzily does this is that it relies on its own internal like intermediary language called Fuzzyl, which can only express syntactically valid JavaScript. So like in the example on the left here, it's missing a bunch of parentheses, so like in the function signature, in that for loop. So that would not be syntactically valid. You also want to ensure semantic correctness. So essentially, this is any program that raises an uncaught exception is considered to be semantically incorrect or just simply invalid. So so in this example here, basically, like, what is the code doing? It's not doing what it's supposed. The code is not doing what it's basically supposed to be doing. So in this calculated average, we see that the syntax is fine, but it takes in these 3 values, but it just never divides by 3. So the actual semantics of that function are wrong, even though it's not going to actually error out. So that one's a bit trickier, and they just left it up to each fuzzing engine. Cool. All right. Fuzzyl, this is kind of like the bread and butter of Fuzzily. Essentially, like I mentioned, it's Fuzzily's own custom intermediary language, or IL, that mimics the JIT compiler's IL in various JavaScript engines. So maybe you have like V8 or JavaScript core. So Fuzzily, what it'll do is it'll exclusively operate on Fuzzyl programs internally, and then only lifts them to JavaScript for execution. So that's kind of like in the top right here in the blue, just like that's basically it. It just generates the code, lifts it, and then executes it in the engine. Basically, this looks like a lot, but it's not too bad really. It's pretty like one-to-one actually. On the left here, this is an example of a Fuzzyl program. It's basically just like a list of instructions. And if you see here, we have this like begin plain function definition and end plain function definition. So the begin is like the start of our function right here. And then we see that it's returning v0, which is our f0. And it takes in v1, v2, v3. So that's our 3 inputs right here. And then it does a binary operation on v1 and v2 and adds them and stores them in v4. So that's what this line is here. And then it just sets the property of v3, or the property called foo of v3 to v4. And then in the bottom here, similar. This is a one-to-one correlation, so v5 is v5. It loads that string hello world, loads this object, loads an int or float, and then calls f0 with those values. So yeah, that's what it would look like after. Cool. And then, that's the next slide, right? Did I miss one? Oh, I did. Whoops. Okay, cool. So yeah, this is kind of just some, I don't know, they're not too relevant, but just examples or code snippets. So each program or the program class will like represent an immutable code of immutable unit of code, which various operations can be performed onto. That's the public let code. And then it also has a unique identifier. I think the comment says it can persist. I'm not actually sure if it can. It persists across like different fuzzer instances. I don't think it should be able to. And then since fuzzy programs are immutable, when they are mutated, they're copied while mutations are like applied, which is done in Program Builder. Yeah. I don't think much of this code is very relevant to the actual mutations, but yeah, this is kind of like or this is just two like big classes that are responsible. And then go to the next one. Yeah, cool. And then this is just kind of a list of like all of Fuzzili's like main mutators, or the mutations that it can perform on its fuzz-IL. I'm not going to go over everyone, but I think some interesting ones are code or splicing. Basically, it'll just copy like a self-contained part of a program, or it could be even the whole program into another one in order to combine the features. And yeah, these runtime ones are also kind of interesting. They just rely on the fact that you have to run the JavaScript in the engine to get back runtime type information. And then based on whatever it's trying to do, for example, like probing, it might like use, probing will try to like determine what properties exist within an object, or I guess it's prototype. Yeah, and it needs the runtime type information to be able to like actually test out properties and see if those properties are valid within the object's prototype, or for that object. Yeah. I'll leave those there. I don't think there's much else on that slide. Yeah, this isn't too much either, but it's just kind of the base class for the mutator. So instruction mutator can mutate, and then the main function or the public func mutate, which will actually get overridden by the child class for the actual like implementation of the mutator. So that's what you kind of look for if you're like looking for the mutators in the code base. Cool. There's a bit of bigger slide. Okay, so I'm just going to go over one of the engines that Fuzzily has. It has another one called Hybrid Engine, but I will just go over Mutation Engine because it's just like simpler, and I don't think it's completely relevant to go over Hybrid for this presentation at least. So yeah, Mutation Engine is like the most basic type of engine that Fuzzily has. It'll essentially just perform n consecutive mutations on like a selected program and look for coverage or semantic errors. So that's what it's doing on the left here. It's just looping max attempts times. If it succeeds, then it will, if it succeeds, then it'll check if it triggered new coverage. If it does, it'll add it to the corpus. Otherwise, it'll just keep looping. And then if it fails, it'll just try another mutator. Yeah. I should note, like, a major limitation of Mutation Engine is that it'll struggle to find bugs or programs that require like a specific sequence of n mutations from some original program that you're mutating off of. Yeah. Okay, cool. I guess I'll also mention that like Hybrid Engine basically just like combines code generation with existing mutators. It's kind of like the high level overview of that. Cool. And then how much more? I think I have 2 more. Okay. Cool. So type system and type inference. So Fuzzily will basically has like this optimization called type inference that improved the effectiveness of like code generators and mutators by reducing the amount of invalid code that gets generated. So it'll infer the types of variables, and then the fuzzer can produce, or I guess by inferring the types of variables, the fuzzer can produce more realistic and valid programs, leading to like more successful fuzzing runs. And yeah, so we can see here, suppose on this one, it doesn't have type inference, and it does b.call function, and it passes an f, where f is just a random variable, not a function. So in our fuzzil here on the right, when we see, it'll like load the string, and then it'll get a type error because it tries to call a function when in reality it's just a random variable. Yeah. And then I guess, wait, go back one more? I'll just like say one more. I guess with type inference, or I guess this is the problem that type inference should fix. Yeah, I mean, that wasn't that bad. Cool. And then this is just kind of like the core components of Fazili. I'm not going to go over each one, but I think some interesting ones are definitely like the evaluator, which will basically like determine if like a program or sample here. Oh, you're good. It'll just basically determine if a program is interesting according to some metric. So their basic metric is just code coverage. So if the program finds new if it finds new code paths or it finds new edges, then it'll deem that program interesting and add it to the corpus. For our project last semester, we were also trying to like mess around with like what other metrics we could add. So we were playing around with like more like the internal states and like trying to figure out something cool to do with that. And then I guess another interesting one is probably Lifter. I should probably look at this more, but I think that one's pretty cool just because it's like the actual translation from the FuzzIL to JavaScript. And then all like the mutation engine and like hybrid engine and the mutators are all also pretty cool to look at if you're interested.
Before we go on to the next section, I think it's worth just explaining why we're talking about any of this and what we actually did last semester a little bit more. Yeah, it's like a little TLDR. First of all, if this is like boring, I apologize. This was also compressed like crazy. This was like a 3-hour presentation from like the start of last semester, where we started this research project and kind of kicked it off with this amazing slideshow and all this stuff. But what we really wanted to do, and what the goal of all of this was to try to find compiler bugs in JavaScript. And the reason any of this matters, and why specifically JavaScript, is every time you load onto a website, most websites are using JavaScript. Most engines themselves actually run JavaScript, right? The website you're running, or the web browser you're using, has its own custom JavaScript compiler and JavaScript interpreter. And a very powerful exploit scenario, right, is somebody logs onto a website or it goes to your website and their entire computer's gone, right? In terms of they get hacked, and this is the way this is actually done. One of the very advanced ways this is done is by actually targeting the JavaScript compilers, right? These are really expensive bugs. These are bugs that when people say, hey, I sold a bug for millions of dollars, this is kind of what people are talking about. The full chain, at least, the renderer bugs are probably a good bit less, maybe like 100, 200K. That's the actual compiler. But regardless, it's they're cool. They're really powerful bugs, and there's an entire industry and job market for this. But yeah. The other thing we actually really wanted to do was there was, if any of you guys remember Sharad from last year, he did a competition called AIXCC. So we kind of wanted to merge both of like the JavaScript fuzzing, attacking compilers with AIXCC. And the idea there was using AI to augment fuzzing and improve fuzzing. And that was like kind of the whole last semester for us, where we were taking this really complicated fuzzer that targets this compiler and improving the fuzzer in very standard ways in terms of, hey, we're getting more information about the compiler through compiler heuristics like Alexei was talking about. And improving the fuzzer's execution speed and all the standard stuff, but it was also like, hey, we're making this really complicated AI systems. And part of that was inspired by Trail of Bits as well as Team Atlantis in terms of their AIXCC systems. And it's kind of why we're talking about this next. But yeah, if any of this interests you, please come to VRig. We meet every Wednesday. It's a shameless plug, yeah, but we meet every Wednesday, Thursday, and we do more fun stuff like this. We're currently Monday, Thursday, you're right. Fuck. Different days now. But yeah. I don't know why I said Wednesday, I'll be honest here. But we're doing allocator security research and looking into designing allocators and doing like a little competition before going back to compiler exploitation. But yeah, really quickly to go over what Trail of Bits' AIXCC system looked like. we had the initial seed generator. So what this would do was it would find and create harnesses as well. And this is all done through AI. So the idea is you throw it into a code base. You have this really complicated code base. You're given a harness before the system actually runs. It's kind of just the format of the competition. But the idea is now, okay, you want to create and generate initial seeds that are useful. You want the fuzzing harness to run. You want to get information on the seeds that you actually generated. After that, you want to maybe explore the code base a little bit, and then you want to generate new seeds based off exploring the code base and trying to find bugs. And then you also have an AI system that fully agentically goes and tries to find bugs by itself. But yeah. This is kind of like the overview of how it works. You have start seed in it, load harness in its initialize task state, context retrieval loop. If we need more context, we'll run our AI system. It can make tool calls, get function, get type definition, cat the file, get callers, batch tools. Then we retrieve the snippets and we give it back to our AI system in order to generate seeds and execute in a sandbox and then save those seeds. But yeah, so the idea is we're essentially allowing AI to autonomously generate input seeds, and then it goes through the code base and also autonomously finds interesting inputs. So the next thing you also have is seed explorer, which it'll load a target function, go through the function, try to understand the function, and if the function is possibly exploitable or see something interesting inside of that function, it can also generate test cases and inputs to try to exploit that. You're not really exploiting it. I guess that's a misnomer. You're more so trying to just get that initial bug and initial crash from the harness. And then vulnerability discovery is the actual, like, hey, let me try letting AI go full on schizophrenic and try to find a bug. Obviously, it's not exactly that. It's a lot smarter. But the idea of vulnerability discovery here is that we're going to go through, let AI analyze the code base and system and try to find bugs and then submit it. Yeah. This was like their main AI system. It's a kind of cam slide. I don't know what he's talking about near the end. I'll be honest. I don't know why there's a Martin Luther. Yeah, what is going on here? Yeah. But really the idea was, hey, how can AI be included in novel security research, and how can you improve the way modern fuzzers work is what two teams kind of did, which a lot of the other work was also how can we fully use AI to find bugs, and a lot of companies now are trying to do that, and there's like this kind of global arms race to make these cool AI hack systems to find bugs. But yeah. I think that's it for me. It's the end of our... You have anything to say?
No, I don't think so.
Thank you.
Does anyone have any questions, I guess?
Oh, yeah, questions. For chance. All right, fair enough.
Cool. Thank you.
Thank you, thank you, thank you.
Okay, that's the end of the general meeting for today. Thank you for coming, everyone. If you open one of the wells in the ground, please make sure you put that back the way you found it. I don't think there are any other reminders that I have for you. So, thank you for coming in. Have a great weekend.